It's late summer at a Japanese apiary, early in the morning, and a beekeeper walks up to one of the hives, where the first thing he notices is the silence. The hive that was humming with thousands of bees just yesterday has gone quiet. So he lifts the lid, and at the bottom, in a layer several inches deep, he finds bodies, thousands of them, and most have no head. He doesn't find the culprits at the scene, though there were fewer than 30 of them, none bigger than his own thumb, and wiping out an entire colony took them less than 6 hours. What kind of creature can erase a colony of thousands of bees using nothing but its jaws? People who've survived its sting describe it the same way every time, like being stabbed with a red-hot needle. What actually happens inside the human body in that moment? And is this really the most dangerous venom among all stinging insects on the planet? At one point, this insect turned up somewhere it had never been before, on another continent, among bees that had no idea it even existed. How did it get there? What happened next? And is it still around? And somewhere between lab data and news headlines, it picked up a name that spread around the world: the murder hornet. Did it earn that name, or does the name say more about us than it does about the insect? By the end of this story, you'll have answers to all 4 questions, and probably not the ones you expect. And we'll also come back to exactly where we started, to that same apiary, and you'll find out what happens there every single year. Let's start with the basics. Vespa Mandarinia is the largest hornet species on the planet. An adult can grow to about 2 inches long, and its stinger measures nearly 1/4 of an inch. And its natural range covers the mountain forests of Japan, along with Korea, Taiwan, China, and parts of South Asia. Warm, humid regions where it has lived alongside local bee species for millions of years. In Japan, it goes by several nicknames, and all of them speak for themselves. Tigerhead, for the distinctive yellow and orange pattern on its face, and yak killer, a nickname so literal it needs no explanation. Long before Western journalists coined the name murder hornet, local people already knew exactly what they were dealing with. Like any wasp, this species lives in colonies with a clear seasonal structure. In spring, a single queen who has survived the winter chooses a shelter, usually an abandoned rodent burrow underground or a cavity in a rotting tree trunk, and builds the first cells of the future nest entirely on her own, raising the first batch of workers without any help. Only once those first workers reach adulthood does the colony's pace really pick up. They take over hunting and building, while the queen focuses on one task alone: laying eggs. And by late summer, the colony reaches its peak population, and in autumn, it produces a new generation of queens and males, which leave the nest, mate, and start the cycle over again. The old colony, including the founding queen herself, dies off completely with the arrival of winter, and only the young, already mated females survive, each one overwintering under tree bark or in leaf litter entirely on her own, ready to start everything from scratch the following spring. So far, this sounds like the ordinary life story of a social insect. And for the most part, it is, until late summer arrives. That's when the colony's food needs shift sharply. The young larvae of that final, largest generation need enormous amounts of protein, and the adults can't eat solid food at all because their jaws are built for cutting and killing, not chewing. So every hunt follows the same pattern. Workers catch prey, tear it apart, and bring it back to the larvae as ready-made meat paste. And the larvae digest that mass and produce a nutrient-rich fluid they then use to feed the adults back. A closed loop. Other social wasps run a version of this same system, but the sheer scale and coordination of Vespa Mandarinia's autumn hunts push it into an entirely different category. And at the peak of the seasonal protein demand, these hornets find the best source of concentrated meat the forest has to offer: a beehive. Thousands of adults and even more larvae in one place, with no need to track down prey one by one. And that's exactly where the story that gave this insect its grim reputation begins. An attack on a hive doesn't happen spontaneously. It's a well-rehearsed sequence, two clearly separate stages, and understanding that sequence explains why the victims almost never manage to react in time. First, a lone scout does the work. She finds a suitable hive and, before flying off, leaves a mark on it, a scent signal that other bees read as the smell of a predator, while other hornets from her own colony read it as an invitation. There's something worth taking here. The scout returns to the nest, and shortly after, a group arrives at the marked hive, usually 20 to 30 individuals. From this point on, the second stage begins, what entomologists call the slaughter phase. The hornets land at the entrance and start killing defenders one after another, biting off their heads with their powerful jaws. A honeybee can only sting once, and only if she manages to get close enough, since the hornet's thick, chitinous armor makes a single sting almost useless against her. And the count isn't measured in units, it's measured in thousands. A group of 20 to 30 hornets can wipe out a colony of 5,000 to 25,000 bees in 1 to 6 hours. Once the last defender falls, the hornets move inside and turn to the reason this all started: the brood, carrying larvae and pupae back to their own nest, where they become exactly the concentrated protein needed to raise that final autumn generation. A hive that was a living organism with several thousand members that morning becomes an empty shell by evening. For a beekeeper facing this for the first time, the scene looks like an inexplicable catastrophe. But behind it lies a cold, almost industrial logistics chain. Reconnaissance, marking, mass assault, resource extraction. So do bees have any answer to this at all? The answer depends entirely on which bee species you're talking about. And that difference becomes the key to everything that happens next. In those same forests where Vespa Mandarinia hunts, lives a native bee species, Apis cerana japonica, the Japanese honeybee. And it has shared this territory with the hornet for millions of years, long enough to develop something most bees in the world don't have: a defense that actually works against this specific predator. When a scout hornet approaches the entrance of a Japanese honeybee hive, there's no panic and no fleeing. Several hundred worker bees, researchers have recorded groups ranging from a few hundred to more than 500, completely surround her, forming a living ball. And at the same time, they start vibrating their flight muscles to generate heat. So inside the ball, the temperature climbs to nearly 115 to 117 degrees Fahrenheit, while the concentration of carbon dioxide from the bee's own breathing rises sharply. Here's the mechanism. Heat at that level, on its own, is something the hornet can survive for several minutes. But combined with an elevated carbon dioxide concentration, her survival threshold drops sharply, and the heat and the suffocating atmosphere hit her system at once, so the predator usually dies inside the ball in under 10 minutes. Lab measurements show the bees themselves have a higher death threshold under the same conditions, several degrees above the hornets. And that difference is exactly what gives the bees their safety margin. What matters most here is that this defense works specifically against the lone scout before she manages to get back to her colony and pass along the signal. And if the bees take her out at this stage, the massive attack phase simply never happens. The hive doesn't survive because it can defeat 30 hornets in open combat. It survives because it breaks the reconnaissance chain right at the start. But there's a crucial caveat. This defense is the result of two specific species, the Japanese honeybee and the Asian hornet, co-evolving on the same territory over an enormous stretch of time, which automatically raises a question. What happens when the hornet meets a bee that never had those millions of years to prepare? The vast majority of bees kept by beekeepers around the world today belong to a completely different species, Apis mellifera, the European honeybee. And researchers who tested her behavior under the same conditions that trigger the heat ball in the Japanese honeybee got a clear result. She simply doesn't show this behavior at all. She never faced the evolutionary pressure that would have pushed her to develop a defense specifically against Vespa mandarinia, because the two species never crossed paths in the wild. And that brings us to an event that didn't happen in the ancient forests of Asia, but very recently, on the other side of the world. August of 2019, Vancouver Island, British Columbia. Local residents discovered a nest of large, unfamiliar hornets and destroyed it, with no idea that they had just witnessed the first confirmed appearance of Vespa mandarinia in North America. And a few months later, in December of that same year, a dead specimen of the same species turned up on the other side of the border in Washington state. How the hornet crossed the Pacific still isn't known for certain. The most likely explanation is accidental introduction. Mated queens may have arrived in cargo shipments along with soil or plant material. And genetic analysis of the specimens found in Canada and the United States showed these were, in all likelihood, two separate, unrelated introductions from different countries of origin, meaning the hornet reached the continent not once, but at least twice. For the local ecosystem, this was a completely new threat. The European honeybee, kept by American and Canadian beekeepers, had never faced a predator of this scale before. No heat ball, no adapted defense, and beekeeping operations across the Pacific Northwest suddenly found themselves in the same position as that colony described earlier, only now without millions of years of a head start to adapt. The news quickly spread well beyond the entomology community. A major publication dubbed the insect the murder hornet, and that nickname spread around the world almost instantly, outpacing any scientific research on the species itself, and the headlines were followed by a wave of public alarm. People reported mass encounters with ordinary, harmless local wasps, mistaking them for the new killer. Amid the panic, Washington state authorities launched a methodical operation stretching over several years. Volunteers set traps across the northwestern part of the state. Entomologists attached radio trackers to live captured hornets to follow them back to their nests. And thermal cameras detected underground colonies by picking up the temperature difference between the nest and the surrounding soil. And by the end of 2021, 4 nests had been located and destroyed in Whatcom County. Two kinds of concern ran through this story from the beginning, and it's worth separating them clearly. One was legitimate. The economic and ecological risk to beekeeping and local pollinators was completely real. And the other was inflated by headlines and unsupported by statistics. Mass anxiety over the lives of people living thousands of miles from the one confirmed outbreak. So what does the venom actually do? The venom of Vespa mandarinia is a complex mix of at least 5 active components. Acetylcholine and histamine cause intense pain and rapid tissue swelling. Kininins dilate blood vessels, speeding up how quickly the venom spreads through the body. And mastoperin and phospholipase work together, destroying immune system cells and triggering extensive inflammation at the sting site. Japanese entomologist Shunichi Makino, who spent decades studying these insects, described the feeling in a single phrase: like having a red-hot needle driven into your skin. And according to him, the affected area keeps throbbing and aching for several more days afterward. With multiple stings, an attacking group can sting a person dozens of times in seconds. The consequences go far beyond local pain. Medical literature from Japan and China has documented red blood cell destruction, muscle tissue damage, acute kidney failure, and shock. And in people prone to allergic reactions, even a single sting can trigger anaphylaxis. There's also a rare and disturbing case recorded in Japan in 2020. A person suffered eye damage after hornet venom hit them directly in the eyes. The insect had sprayed it from a distance rather than delivering it through a direct sting. These factors explain why, by some estimates, Vespa mandarinia is considered the deadliest animal in Japan. Depending on the source, somewhere between 10 and 50 people die there from its stings every year. And in China, the death toll has also reached the dozens in some years. But here's where the emphasis matters. According to toxicology research, this hornet's venom is nowhere near the most potent among stinging insects in the world. Measured by equal volume, it's actually less toxic than some much smaller wasp and bee species. And the danger doesn't come from an exceptionally powerful venom. It comes from the sheer amount delivered in a single sting. Because of its size, this insect injects far more venom than any other stinging species common in North America or Europe. And a weak venom in a large dose can cause comparable harm to a strong venom in a small one, just for completely different reasons. There's another detail that almost never makes it into the scary headlines. Entomologists who've studied this species for years agree that hornets show almost no interest in humans while hunting, and in the vast majority of cases simply ignore people if left alone. And real aggression kicks in almost exclusively when someone approaches or disturbs the nest. Most of the death statistics in Japan involve people who accidentally stumbled onto a nest in the woods or disturbed one while working the land, not deliberate attacks on people going about their day. It's precisely because of this gap between the real risk profile and the media image that North America's entomological community officially revised the species' common name in 2022. The reason for changing it from Asian giant hornet to northern giant hornet was stated openly. The regional reference built into the name was fueling anti-Asian sentiment that had intensified during the pandemic, and creating a stigma that had nothing to do with the insect's actual biology. And around the same time, scientists also revised several other insect names that carried similarly painful associations. The murder hornet name didn't go anywhere, of course. It rarely does. Let's close this out not in America, but back where we started. The scene from the very beginning of this story, the ravaged hive, the silent apiary, the headless bodies, wasn't a reenactment of some rare occurrence. It's a routine, recurring scene for Japanese beekeepers every autumn, part of their professional calendar for centuries. Where Vespa mandarinia has lived since ancient times, this threat isn't a sensational headline. It's a well-known seasonal risk, one for which methods of defense already exist. Simple baited traps, selectively breeding bee lines capable of forming a heat ball. The story played out very differently on the other continent. After 5 years of traps, thermal cameras, and radio trackers, the Washington State Department of Agriculture, together with a federal agency, officially announced that, following 3 years without a single confirmed sighting, the northern giant hornet had been declared eradicated from the United States. One of the officials leading the effort remarked at the time that this was one of those rare occasions when humans actually win one against insects. And behind the official announcement lay years of painstaking, often invisible work by hundreds of volunteers and scientists. But even here, the story ends with an ellipsis rather than a period. That same autumn, shortly before the victory was announced, a report came in from Kitsap County of a possible encounter with a similar insect, and specialists were never able to obtain a specimen to confirm it, so the sighting remained unverified. Officials summed it up with a line that became this whole story's unofficial motto. They got here once, and they could very well do it again. So what have we actually learned? We saw a predator whose tactic for wiping out entire colonies has been refined over millions of years, and a bee that, over that same span of time, found a way to fight back, but only on its own territory and only against the one enemy it managed to adapt to. And we traced how a chance event, a handful of mated queens in a cargo shipment, turned a local threat into an intercontinental story that grew far bigger in the headlines than the actual damage it caused to people outside Asia. And we saw two completely different endings to the same species story. In Japan, year after year coexistence with a familiar danger. In North America, a brief, nearly 5-year panic that ended in an official victory, one that still offers no absolute guarantee for the future. Here's a question worth putting to you directly. If a new invasive species with a similar reputation showed up in your region tomorrow, what would scare you first? The actual risk statistics for you personally, or the image the first headlines would create? Tell us in the comments which one would win out and why. The northern giant hornet is no longer on the list of threats to American apiaries, but at the Japanese apiary where this story began, a new hunting season will start again this very autumn, just as it has started every autumn for a very, very long time.